So now Professor Jama Mohamed Sharif will present us his work entitled Identification of Structural Damage on a Circular Plate Excited at Ultrasonic Frequencies using Scanning Laser Vibrometer Measurement. Professor Jama, you have 10 to 15 minutes to present us your work. You can start, please.
Thank you, Chairman. Good morning, everyone. I'm Professor Jama of the Laboratory of Mechanics and Structure of the University of Galma. I'm mainly interested by the source localization and identification of damage in structure using inverse programs. Donc, I will present today recent work which is carried out in part in the LVA, Laboratory of Vibration and Acoustic of Lyon in France. My presentation is entitled Identification of Structural Damage on a Circular Plate Excited at Ultrasonic Frequencies using Scanning Laser Vibrometer Measurement. Donc, I will present an overview of structural damage identification, an overview on direct and inverse problem formulation. I will present numerical results, and then I will present the new idea using LEM waves. And I will present the experimental setup, which is carried out at LVA of LINSA, and I will conclude by some conclusions. We're going to detect the damage in structure. We have two ways. The first is the use of direct problems to detect the damage. In this case, we use the excitation of structure, and we take come output displacement velocities or other indicator. We use different methods such as FM method, analytical method, and in reality measurement. In the inverse program, which is my interest, the inputs are obtained by measurement, like displacement, velocities, and so on. And then we try to identify the damage, dimension, position, and so on. The structural damage identification method, various inverse methods are used, such as the work presented by 2erjour, in which an inverse identification approach using finite difference method is used, and then the higher order spatial derivatives are very sensitive to the presence of structural damage in a beam, as well as the damage index. Other researchers, like Ableiser, use the RIF method to identify the stiffness and damping of an isotropic plate. Recently, Disperse et al. Are demonstrated that the damage can be directly observed in the dispersion curves due to the sensitivity of LEM waves to small thickness variation of plate. If the thickness varied, the LEM waves change. And recently, based on the sensitivity of LEM waves, Edge et al. Use the method CFAT methodology to estimate thickness loss defect on flat plate within the ultrasonic frequency band to identify the wave numbers of symmetric S0 and antisymmetric mode of the LEM wave. In my case, I have used the circular plate, which the equation of motion is governed by this equation. And we can remark that the existence of 4 derivatives on displacement by resolution of the equation, by introduction the displacement in the equation of motion, we can obtain equation on terms of frequencies, and we can identify the damage if the index damage equal if the index damage is different to 0, that significated the existence of defect. If the AD equal to 0, the structure is undamaged. The idea is to discretize the 4 derivatives in terms of displacement by finite difference method, and then we can calculate the index damage at every point on the structure. For our case, the disc is an aluminum alloy disc with external diameter of 218 millimeter, and so and the thickness is 3 millimeter. With the meshing steps is in the radial direction of the 5 millimeter, and the angular direction is to the 6 degrees. By using the IDS software, we have obtained the frequencies, the 10 first frequencies, and we obtain the mode shape of different modes. As your marks, there is symmetric and anti-symmetric mode. There are the same frequency, and we have other mode which are not symmetric. When calculating the AD for this case, we obtain this mass, and we can remark that the AD is different of 0, or the disk is undamaged. The problem is in radial direction the step is regular, but the linear steps on the angular direction is not regular. For this reason, the 4 derivatives introduce some error, and then we cannot obtain good results. We continue with an undamaged disk, and we obtain the results in terms of frequencies. The frequencies when the disk is damaged are shifted in lower frequencies, like the first one or the other. This indicates that the disk is damaged, since the frequencies are shifted. We have stopped the simulation at this step because the results with undamaged disk not give the good results. We have stopped the work in this stage. The proposed methodology is to use the characteristics of lamp waves, which are sensitive to the thickness, the variation of the thickness. Donc using for in flat plate, we use these equations. At work of Edge et al. Recently, the dispersion curve of lamp waves demonstrate that this dispersion curve are a function of variation of the thickness of the plate. If the damage is characterized by a loss of thickness, the lamp waves detect this variation. The symmetric, it exists the mode symmetric mode and anti-symmetric mode. The behavior of the two lamp waves is different in face of the loss of thickness. The experimental setup, we have the disc, we have the aluminum disc with a defect created voluntarily. It is a hole with 0.6 millimeter. And we have the actuator, the piezoelectric actuator here. And we have the laser for measurement of the zone in which the disc is in which the damage exists. We have measure in the other phase. We measure the velocities around the defect. The primary results, I use the screenshot. We have here, this is the disc, this is the zone inspected by measurement, and this is the defect. Without any treatment, at high frequencies, the lamp waves are very sensitive to the variation of the thickness, and we have detect the position and the dimension of the defect ASIM. In conclusion, the piezoelectric actuator which work at ultrasonic frequencies, as well as the continuous scanning laser as a measurement tool, are used in this work. The identification of damage at low frequencies by inverse method. Like Riff method, which I have used in the past, is difficult, in particular in the case when using the measured velocity or displacement, because the noise is amplified by the fourth order derivatives. However, the identification of damage at ultrasonic frequencies is possible, since the lamp waves are very sensitive to the local thickness variation, density, or elasticity modules, which represent the damage. Preliminary results without any treatment show that the damage is observed at the exact position and with exact dimension. In perspective, we will consider the general case where the measured velocities are mixed with noise and its influence on the identification results. To compute the damage index in order to obtain the exact position of the damage, it will be necessary to compute the wave numbers according to the measured velocity with the applied of signal processing to obtain good results. Thank you for attention.
Thank you, Professor Jama, for your clear exposition. So, if you have any question, please.
Assalamu alaikum. Really, I would like to start by thanking the organization of this event. So, the second hand, thank you, Mr. Professor Jama, for the clear and interesting presentation. My question is regarding this approach. If we can use this approach for more complex geometrical, like for example, the pipeline used in oil and gas industry, or tank used in which taking in the account the complexity of geometrical of this installation, and also the condition of position of those instruments.
Thank you. The lump waves are particular waves which propages in structure like plate. I think with the pipe, which the direction are linear, I suppose that this method can be applied. But for complex structure,
The problem with the pipeline, we know that they have long length, and especially and also for their position. Sometimes we find that the hydrocarbon pipeline are easily accessed, and sometimes we cannot access for the pipeline because it's buried under the ground. And also for the tank, that in order to have an idea or the establish the monitoring of the integrity of those equipment, we need to an approach that can give a general approach for the integrity of those structures, which is big. We compare with the small link.
Pour la technique, donc il faut que la possibilité de mesure, il faut accéder à la surface vibrante pour le cas. Il faut accéder à la surface vibrante pour déterminer les vitesses qui sont c'est-à-dire les outputs les inputs pour notre problème. Et dans ce cas, il faut accéder pour des pipelines qui sont enterrés. Donc je pense pas que la méthode peut donner un résultat tant qu'il n'y a pas de possibilité d'aller vers la mesure des déplacements ou bien des vibrations. Je pense pas.
Another question regarding the residual stress. If we can apply this approach to determine, in other words, the residual stress in the mechanical structure.
Je pense pas puisque ici donc il faut qu'il y ait une variation d'un élément. Bon, soit l'épaisseur, soit les caractéristiques mécaniques. Si par exemple, si la zone par exemple affectée par les contraintes résiduelles, si elle change les caractéristiques mécaniques telles que le module de Young ou bien la densité, etc., ça peut donner un résultat. Ça peut donner un résultat puisque les ondes de lampe sont très sensitives à cette variation, que ce soit l'épaisseur, que ce soit le module de Young, que ce soit... Donc il faut accéder avec un piezo électrique.
Même la propagation de la bombe se doit faire par rapport à un milieu qui est c'est-à-dire celui d'un contrainte ou non.
C'est-à-dire une pièce avec une zone sous contrainte. Je pense que les caractéristiques mécaniques à cet endroit, elles sont différentes. Donc je pense que la structure elle est régulière. Bon, pour le cas, je ne sais pas pour d'autres cas complexes, si c'est une plaque par exemple, ou bien un tuyau par exemple, où il y a la directrice elle est linéaire, je pense qu'il y a cette possibilité. Je pense.
So, is there any other question, please?
Oui, Baptiste.
Expliquez comment vous avez fait l'expérience, c'est-à-dire l'énergie de la laser, quel type de piezoélectricité vous avez utilisé, quelle est l'énergie de laser que vous avez utilisé.
Donc, voilà. Donc je reviens. Bon, pour la mesure, donc ici donc nous avons un excitateur piezoélectrique. Dans la fréquence, elle peut aller jusqu'à 2 GHz.
Quel type de mesure de ce piezo?
Ah, ça c'est une. Bon, il y a comment dire, il y a le type, c'est EPZ, etc. Donc je pense pas de. C'est-à-dire, je n'ai pas y aller chercher sur le. C'est un piezo, pour nous, c'est pour l'excitation. Je ne cherche pas à comprendre, c'est que je cherche uniquement la fréquence d'excitation pour aller jusqu'à. C'est-à-dire trouver c'est-à-dire les fréquences les plus hautes possibles. Le laser, c'est un instrument. Pour moi, c'est un instrument de mesure.
Oui, il y a plusieurs énergies de laser.
Oui.
Il y a plusieurs énergies. Il y a les fortes énergies, les
Non,
Quelle valeur?
Non, si vous utilisez le laser pour excitation. Pour l'excitation, je comprends, ça dit l'excitation avec un laser, ça dépend de la densité, de l'effort émis, etc. Mais pour nous, c'est un instrument avec un réglage bien déterminé. Je mesure les vibrations.
Et non, pour avoir des vibrations, il faut coupler le laser avec le piezo, le matériau piezoélectrique, le doublage.
Non.
Entre l'énergie de laser et le type de piezo. C'est-à-dire le matériau piezoélectrique.
Non, il n'y a pas de liaison. La liaison, c'est quoi? Vous avez un excitateur dans une bande de fréquence déterminée. Le laser, il va capter les vitesses vibratoires dans cette bande de fréquence. Il n'y a pas de réglage spécifique. D'accord? Il n'y a pas de réglage spécifique. Il y a un excitateur dans une bande de fréquence bien déterminée et vous avez le laser pour capter les vibrations résultantes.
Okay, thank you, Professor Jama, for your clear and interesting presentation. So, the next one, please.